Somewhere out there, about 23 light years from where you are right now, there is a planet that some scientists believe could be one of the most Earth-like worlds we have ever found. It orbits not one, not two, but three different stars. And the truly remarkable thing is that this planet sits in a place where liquid water, the ingredient we believe is most important for life, could actually exist on its surface. Its name is Gissa 667 cc, and tonight we are going to explore everything we know about it. Now, before we go any further, let me be honest with you. When scientists say a planet is habitable or Earth-like, they do not mean you could step off a spaceship and breathe the air. They do not mean there are forests and oceans waiting for us. What they mean is that the conditions on this planet might allow liquid water to exist. That is the starting point. That is the door that opens every other possibility. And Gissa 669 cc has that door standing wide open. But here is where things get really interesting and maybe a little unsettling. Because while this planet checks so many of the boxes we look for when searching for a second home among the stars, it also comes with some serious challenges. Challenges that make you wonder whether the universe is teasing us, showing us something beautiful and then placing it just out of reach. So settle in, get comfortable. Let the world around you go quiet for a while. Because tonight, we are going on a journey across 23 light years of space to a world bathed in the glow of a dim red sun, where the sky holds not one but three stars, and where the line between day and night might hold the secret to life beyond Earth. Let us start at the very beginning. What even is Gissa 667 cc, and how did we find it? To understand this planet, we first need to understand the star it orbits. Actually, we need to understand three stars, because Gissa 667 cc does not live in a simple solar system like ours. It lives in a triple star system. That means three stars, all bound together by gravity, all dancing around each other in the darkness of space. The system is called Gissa 667, and it sits in the constellation of Scorpius, which you might know as the Scorpion. If you have ever looked up at the night sky on a clear summer evening and found that hook-shaped pattern of stars near the horizon, you have been looking in the general direction of this system, although you would never see it with your eyes alone. The stars are too faint for that, but they are there, just 23 light years away. Now, 23 light years might sound close in the grand scheme of things, and in cosmic terms, it really is. Our Milky Way galaxy is about 100,000 light years across, so Gissa 667 is practically in our neighborhood. But do not let that fool you into thinking we could visit anytime soon. Even our fastest spacecraft, the Parker Solar Probe, which can reach speeds of about 430,000 miles per hour, would take over 350,000 years to get there. That is longer than our entire species has existed. So when we talk about Gissa 667 cc, we are talking about a place we can study, we can dream about, but we cannot touch. At least not yet. The three stars in this system each have their own personality. The biggest one is called Gissa 667a. It is what astronomers call a K-type star, which means it is a bit smaller and cooler than our Sun, with about 65% of the Sun's mass. It glows with an orange hue, putting out only about 12 or 13% of the light our Sun produces. Next to it, orbiting in a close dance, is Gissa 667b. This one is also a K-type star, even a little smaller than A, with about 45% of the Sun's mass. These two orbit each other at a distance of roughly 12.5 times the distance from Earth to the Sun. swinging as close as 5 times that distance and as far apart as 20. Their orbit takes about 42 years to complete. But the star we really care about is the third one, the quiet one, the small one that sits far away from the other two, orbiting them at a distance of about 230 times the Earth-Sun distance. That is roughly 6 times farther than Pluto is from our Sun. This little star is called Gissa 667c, and it is a red dwarf. Red dwarfs are the most common type of star in our galaxy. They are small, they are cool, and they are incredibly long-lived. While our Sun will burn for about 10 billion years before it runs out of fuel, a red dwarf like Gissa 667c could potentially shine for 100 to 150 billion years. That is 10 to 15 times longer than our Sun. To put that in perspective, the entire universe is only about 13.8 billion years old. So these little red stars could keep burning long after most other stars in the galaxy have gone dark. Gissa 667c has about a third of the Sun's mass and about a third of its width. Its surface temperature is around 3,400 degrees on the scale scientists use, which is significantly cooler than our Sun's 5,500 degrees. Because it is so small and cool, it puts out only about 1.4% of the light our Sun produces. If you replaced our Sun with Gissa 667c, the Earth would freeze solid in a matter of days. But here is the thing about red dwarfs. Because they are so dim, the zone around them where liquid water could exist on a planet's surface, what scientists call the habitable zone, is much closer to the star. In our solar system, Earth sits about 93 million miles from the Sun. Around Gissa 667c, the habitable zone is about 10 times closer. It is so close that the entire habitable zone fits inside the orbit of Mercury in our own solar system. And that is where Gissa 667cc lives, right in the sweet spot. This planet was first detected in November of 2011 by a team of astronomers using an instrument called HARPS, which stands for High Accuracy Radial Velocity Planet Searcher. It is attached to a telescope in Chile, high in the mountains where the air is thin and clear and the stars shine bright. HARPS does not actually see planets directly. Instead, it watches stars very, very carefully, looking for tiny wobbles. Here is how it works. When a planet orbits a star, its gravity pulls on the star ever so slightly. This causes the star to wobble back and forth, and that wobble shifts the light coming from the star in a predictable way. By measuring these shifts, scientists can figure out that a planet is there, how heavy it is, and how far it orbits from its star. It is an incredibly clever technique, and it has been responsible for finding hundreds of planets beyond our solar system. The confirmation came in February of 2012, when researchers at the University of Göttingen and the Carnegie Institution for Science published their findings. They announced that Gissa 667cc was one of the best candidates ever found for harboring liquid water, and therefore, potentially, for supporting life on its surface. Now let us talk about what makes this planet so special. Gissa 667cc is what scientists call a super-Earth. This does not mean it is a bigger, better version of our planet. It simply means it is larger and heavier than Earth, but still smaller than the gas and ice giants like Neptune and Uranus. Gissa 667cc has a minimum mass of about 3.7 to 4.8 times the mass of Earth, depending on which study you read. Its radius is estimated to be about 1.5 to 1.8 times that of Earth. If you could stand on the surface of Gissa 667cc, assuming it has a solid surface, you would weigh more than you do on Earth. the gravity would be stronger. Not crushingly so. Scientists estimate it would be about 1.1 to 1.3 times Earth's gravity. You would feel heavier, your steps would feel a little more deliberate, but you could still walk around. You could still function. The planet orbits Gissa 611c at a distance of about 0.125 astronomical units. To put that in everyday terms, it is about 8 times closer to its star than Earth is to the Sun. That sounds dangerously close, and if the star were as bright and hot as our Sun, the planet would be a scorched, lifeless rock. But because Gissa 667c is so much cooler and dimmer, this close orbit is actually perfect. The planet receives about 90% of the energy that Earth gets from the Sun. Just 90%. So it gets almost the same amount of warmth we do, just from a much closer, much dimmer source. This means the temperature on Gissa 667c could be quite pleasant. Scientists estimate an equilibrium temperature of about 4.3 degrees Celsius, which is around 39.6 degrees Fahrenheit. That is cool, but well above freezing. If the planet has an atmosphere similar to Earth's, some scientists have suggested surface temperatures could reach as high as 30 degrees Celsius, or about 86 degrees Fahrenheit. That is a warm summer day. But wait. Before you start packing your bags, there are some things you should know about this world that make it very, very different from home. Because Gissa 606m orbits so close to its star, it only takes about 28 Earth days to complete one full trip around it. That means 1 year on Gissa 606m is shorter than 1 month on Earth. Think about that. You could celebrate your birthday every 28 days. If you lived there, you would rack up birthdays faster than you could count them. In 77 Earth years, you would be 1,000 years old. In Gissa 606c years. That is a strange thought. The way we measure time is so deeply tied to the orbital period of our own planet that we rarely stop to consider how arbitrary it is. A year is just one trip around the Sun. On Gissa 606c, that trip is 13 times shorter. The concept of a month, a season, even a week would need to be reinvented, and the calendar would just be the beginning. The entire rhythm of life on this world would be dictated by fundamentally different cycles. On Earth, the cycle of day and night drives almost every biological process. Plants open their leaves during the day and close them at night. Animals wake and sleep according to the light. Our own bodies produce hormones on a roughly 24-hour schedule that governs everything from alertness to hunger to body temperature. All of this is synchronized to the spinning of our planet, to the predictable alternation of light and dark. On Gissa 606c, none of that would apply. With one side impermanent light and the other impermanent darkness, there would be no daily cycle to entrain biological clocks. Any life that evolved there would need to find entirely different ways to organize its internal processes. Perhaps it would respond to temperature gradients instead of light cycles. Perhaps it would have no internal clock at all, functioning in a continuous, unbroken state of activity. Or perhaps it would create its own rhythms, synchronized not to the rotation of the planet, but to some other environmental signal, the slow variation in stellar flares, perhaps, or the gentle oscillation of tidal heating as the orbit changes shape over years. This is one of those details that scientists find endlessly fascinating. The biology of timekeeping, the way organisms track the passage of time and synchronize their activities to environmental cues, is one of the most fundamental aspects of life on Earth. Understanding how this could work on a world without days and nights would teach us something deep about the nature of biological organization itself. but the days would not be like anything you have ever experienced. Because of its close orbit, Gissa 616c is almost certainly tidally locked to its star. Tidal locking is the same thing that happens with our moon. The moon always shows the same face to Earth. It rotates exactly once for every orbit it makes around us, so the same side always points our way. That is why we never see the far side of the moon from Earth. On Gissa 667cc, tidal locking would mean one side of the planet always faces the star. Permanent, eternal daytime. The red dwarf would hang in the sky, never moving, never setting, casting its dim reddish light across one entire hemisphere. And the other side of the planet would face away from the star forever. Permanent, eternal night. Cold and dark and silent. Imagine that for a moment. Imagine a world split in two. One half bathed in a warm, reddish glow that never fades. The other half locked in darkness so deep and cold that the air itself might freeze and fall like snow. There would be no sunrise. There would be no sunset. Just endless day on one side and endless night on the other. This kind of arrangement creates extreme temperature differences. The day side could get quite hot, especially directly beneath the star, which scientists call the substellar point. The night side could drop to hundreds of degrees below zero. Without something to move heat around, one half of the planet would bake while the other half froze. But here is where something fascinating comes into play. Between the permanent day and the permanent night, there would be a narrow band of land, a ring that wraps all the way around the planet, where the light from the star meets the shadow of the night. Scientists call this the terminator zone. The terminator zone is a region of eternal twilight. The star would sit low on the horizon, never fully rising and never fully setting. The light would be dim and soft, filtered through whatever atmosphere the planet might have. Temperatures in this zone could be moderate, not too hot, not too cold, just right for liquid water to exist. In 2023, a team of scientists published a study in the Astrophysical Journal exploring this exact idea. They used climate modeling software, the same kind used to study weather and climate on Earth, to simulate what conditions might be like on tidally locked planets. What they found was encouraging. If a tidally locked planet has the right combination of land and water, the terminator zone could indeed be habitable. Not the whole planet, just this narrow ring of twilight. But that ring could support liquid water, mild temperatures, and potentially life. The key, they found, is balance. Too much water, and the heat from the day side would boil it into a thick blanket of steam that would wrap the entire planet in a suffocating greenhouse effect. But if the planet has more land, especially on the day side, the terminator zone becomes more stable. Ice from the night side could melt as it moves toward the warmer regions, creating lakes and rivers in the twilight zone without triggering a runaway greenhouse effect. This is speculative, of course. We do not know if Gissa 610 has land or oceans. We do not know if it has an atmosphere at all. But the science suggests that these kinds of worlds could work, and that is what makes Gissa 667cc so exciting. It is not just a dot on a chart. It is a real possibility. Now let us talk about what the sky would look like from the surface of this planet, because this might be the most incredible part of all. If you stood on the day side of Gissa 667cc and looked up, the first thing you would notice is the star. Gissa 667c, the red dwarf, would dominate the sky. Even though it is much smaller than our sun, it is much closer. From the surface of the planet, this star would appear about 2.3 times wider than our sun looks from Earth. It would cover about 5 times more area in the sky, but it would look very different. Instead of the brilliant yellow-white glare we are used to, this star would glow a deep, warm red. The light it casts would be soft and ruddy, like the last few minutes of a sunset on Earth that never ends. Most of the light coming from this star would actually be invisible. Red dwarfs emit the bulk of their energy in infrared, which our eyes cannot see. So even though the planet receives nearly as much total energy as Earth does, much of it would be in the form of invisible heat rather than visible light. The visible landscape would be dim, painted in shades of deep red and amber. If plants existed on this world, scientists have speculated they might be dark, almost black, to absorb as much of the limited visible light as possible. But the red dwarf is not the only star in the sky. Remember, Gissa 667 is a triple star system. The other 2 stars, Gissa 667a and 667b, orbit each other far away, about 230 times the Earth-Sun distance from the red dwarf. That is far enough that they would not affect the planet's orbit or climate in any significant way, but they would be visible, very visible. From the surface of Gissa 667cc, these 2 companion stars would appear as a brilliant pair of points in the sky. During the daytime, they would look like 2 exceptionally bright stars. At nighttime, if you could stand on the dark side of the planet, they would shine with the brightness of a full moon, maybe even brighter. They would cast a soft light across the frozen nightside landscape, creating shadows and reflections on whatever ice and snow might cover the ground. And here is something even more magical. Our own sun would also be visible from Gissa 667c. 23 light years away, our sun would appear as just another star in the sky, a faint point of light among thousands of others. You would need to know exactly where to look to pick it out, but it would be there, a tiny spark in the vast darkness, with no way to tell from that distance that a small blue planet orbits around it, teeming with life. Think about that for a moment. Someone standing on Gissa 667cc and looking at our sun would see nothing remarkable, just another star. They would have no idea that around that ordinary-looking point of light, there is a world full of oceans and mountains and forests and cities and people who, at this very moment, are looking back at them and wondering if anyone is there. There is something deeply moving about that, something that reminds us how vast the universe is and how small we are within it. And yet, here we are, reaching out with our instruments and our mathematics and our curiosity, trying to bridge that impossible distance with nothing but knowledge and imagination. Let us go deeper into the science of this planet, because there is so much more to explore. One of the most important things scientists look at when evaluating a planet's potential for life is something called the Earth Similarity Index, or ESI. This is a number between 0 and 1 that describes how similar a planet is to Earth, across several key factors including size, density, temperature, and the amount of energy it receives from its star. A score of 1 would mean the planet is identical to Earth. A score of 0 would mean it has nothing in common with our world. Gissa 667cc has an Earth Similarity Index of about 0.82 to 0.85, depending on the study. That is remarkably high. At the time of its discovery, it was considered the most Earth-like exoplanet ever found. Since then, we have discovered other candidates that score similarly, but Gissa 667cc remains one of the most compelling. But the ESI does not tell the whole story. It is a useful shorthand, but it leaves out many factors that could make or break a planet's chances for life. Factors like the presence of an atmosphere, the strength of a magnetic field, the level of radiation from the star, volcanic activity, and the chemical composition of the surface. These are things we simply cannot measure yet for a planet 23 light-years away. And this is where we need to have an honest conversation about what we know and what we do not know. Because the truth is, most of what we discuss about Gissa 607cc involves a fair amount of scientific speculation, not wild guessing, not science fiction, but educated estimates based on the data we have and the physics we understand. When scientists say this planet could have liquid water, they are saying the math works out. They are saying the conditions are right. They are not saying they have seen water there. When they talk about habitability, they are talking about potential, not certainty. And that is okay. That is how science works. You start with what you can observe, you build models, you make predictions, and then you look for ways to test those predictions. The fact that we cannot yet confirm whether Gissa 607cc has water or an atmosphere does not mean the investigation is pointless. It means we are at the beginning of a story that could take decades or even centuries to fully tell. And the beginning of a story is often the most exciting part. So with that in mind, let us explore some of the challenges this planet faces. Because for all its promise, Gissa 607cc has some serious obstacles that could work against the possibility of life. The first and perhaps most significant challenge is radiation. Red dwarf stars like Gissa 667c might be small and cool, but they can be surprisingly violent. Many red dwarfs are what astronomers call flare stars. They periodically unleash enormous bursts of energy, including ultraviolet light, X-rays, and streams of charged particles. These flares can be incredibly powerful, sometimes causing the star to temporarily double in brightness. For a planet orbiting as close as Gissa 667cc does, these flares could be devastating. On Earth, we are protected from the worst of our sun's radiation by two things. First, we have a strong magnetic field generated by the spinning of molten iron in our planet's core. This magnetic field, called the magnetosphere, acts like an invisible shield, deflecting most of the charged particles the sun throws at us. Second, we have a thick atmosphere with an ozone layer that absorbs much of the harmful ultraviolet radiation. Gissa 667cc might not have either of these protections. Because the planet is likely tidally locked, it rotates very slowly, once every 28 days. A slow rotation could mean a weaker magnetic field, or possibly none at all. Without a magnetic field, the planet's atmosphere would be exposed to the full force of the star's flares. Over millions of years, these flares could strip the atmosphere away entirely, leaving the surface bare and unprotected. This is not just a theoretical concern. NASA's research on red dwarf habitability has shown that intense ultraviolet and X-ray radiation from young red dwarfs can enable the escape of atmospheric gases, including oxygen and nitrogen. In some models, a young red dwarf could render a close-in planet uninhabitable within just a few tens of millions of years by stripping away its atmosphere entirely. That might sound like a long time, but in geological terms, it is the blink of an eye. Life on Earth took hundreds of millions of years to get started. If Gissa 667cc lost its atmosphere before life had a chance to begin, the story ends before the first chapter. But there is hope. In 2021, an international team of astronomers made an exciting discovery. They found evidence that red dwarfs tend to launch their most powerful flares from near their poles rather than from their equators. This is significant because planets orbit in a plane that is roughly aligned with the star's equator. If the worst flares are directed upward and downward, away from the orbital plane, then planets like Gissa 606n cc might be somewhat protected. The radiation would pass over them instead of hitting them directly. This does not eliminate the risk, but it could reduce it significantly. There is another concern that has emerged more recently. In 2013, a scientific paper revealed that Gissa 667 cc experiences tidal heating roughly 300 times greater than what Earth experiences. Tidal heating is caused by the gravitational pulling and stretching of a planet as it orbits its star. On Earth, tidal heating from the Moon and Sun is very mild. But on Gissa 606 cc, which orbits so much closer to its star, the effect is far more intense. The source of this extreme tidal heating is partly the planet's orbit, which is not perfectly circular. The eccentricity of Gissa 667 cc's orbit changes on a cycle of about 4.6 years, shifting between more circular and more stretched out. This constant flexing generates enormous amounts of heat inside the planet. Computer simulations suggest this tidal energy would increase the planet's temperature by about 1.6 degrees every 100,000 years. Over millions of years, this could partially or even completely melt the planet's mantle, covering the surface in lava. Now that sounds pretty bleak. A planet covered in lava is not exactly what comes to mind when we think of a habitable world. But it is important to remember that these are models, not observations. Different assumptions about the planet's internal composition, its exact orbit, and how efficiently it dissipates heat could lead to very different outcomes. Some scientists argue that the tidal heating could actually be beneficial, keeping the planet's interior warm and driving geological activity that could replenish the atmosphere and cycle important chemicals. On Earth, plate, tectonics and volcanic activity play a crucial role in maintaining a livable climate over billions of years. A geologically active Gissa 667 cc might actually have an advantage in that regard. This is one of the beautiful things about science. Even the challenges can have silver linings, and even the obstacles can open new doors. Let us return to the sky above Gissa 667 cc, because we have only scratched the surface of what it would be like to experience this alien world. We talked about the red dwarf star hanging motionless in the sky of the dayside, casting its warm reddish glow. We talked about the two companion stars shining like bright jewels in the distance. But there is more to this picture. Much more. If you stood on the day side of Gissa 667 cc and looked at the red dwarf, you would be looking at a star that is remarkably different from our sun in almost every way. Our sun is a yellow-white furnace that blazes at nearly 5,500 degrees on its surface. It radiates across the full spectrum of visible light, which is why sunlight on Earth appears white or slightly yellow. Gissa 667c, on the other hand, burns at only about 3,400 degrees. At that temperature, the star glows predominantly in deep red and infrared. To your eyes, the landscape would look like it had been painted by someone who only had red, orange, and brown on their palette. The star would appear as a large, soft red disk in the sky, about 3 times wider than the sun appears from Earth, and covering about 10 times the area. But despite its large, apparent size, it would feel dimmer, softer, like being bathed in the last few minutes of twilight on a winter evening that never quite fades to black. There would be enough light to see by, but everything would have a warm, dusky quality to it. Shadows would be long and soft, Colors as we know them would shift dramatically. Blues and greens would be hard to distinguish. Everything would lean toward the warm end of the spectrum. And the heat you would feel would be different too. On Earth, much of the warmth we get from the sun comes in the form of visible light that is absorbed by the ground and the atmosphere and then re-radiated as heat. On Gissa 667 cc, a large portion of the star's energy arrives as infrared radiation. You would feel the warmth directly on your skin, like standing near a heat lamp, even if the visible light seemed dim. The planet's surface, if it has one, would absorb this invisible heat and warm up in ways that might not match what your eyes are telling you. The visual experience and the thermal experience would be disconnected in a way that feels deeply alien. Now imagine you start walking. You leave the substellar point, the spot on the day side directly beneath the star, and you head toward the terminator zone. As you walk, the star gets lower and lower on the horizon. The light gets dimmer. The shadows get longer. The temperature drops gradually. The air, if there is air, might start to feel cooler. You are walking toward the edge of the eternal day, into the region where the light fades and the darkness begins. At the terminator zone, the star would sit right on the horizon. Imagine an endless sunset, stretching all the way around the planet, a band of amber and crimson light glowing along the horizon in every direction. Above you, the sky would darken to deep purple and then black, and the stars would begin to appear. The two companion stars, Gissa 667a and 667b, would shine brightly overhead, a pair of distant suns that offer light but little warmth. The temperature here would be the most moderate on the entire planet, not scorching like the day side, not freezing like the night side. Depending on the atmosphere, it could be anywhere from just below freezing to pleasantly cool. If there is water on this planet, this is where you would most likely find it. Liquid water, maybe flowing in streams or collecting in lakes. Ice from the night side could gradually migrate toward the terminator zone, melting as it encounters the warmer air from the day side. This could create a kind of slow, continuous water cycle, fundamentally different from Earth's, but potentially just as important for any life that might exist. Now keep walking. Pass through the terminator zone and into the night side. The star disappears below the horizon behind you. Ahead, there is only darkness. The temperature plunges. Without the star's warmth, the night side could be hundreds of degrees below zero. Any atmosphere here might freeze and fall as snow, made not of water, but of carbon dioxide or nitrogen. The ground could be covered in layers of frozen gases, smooth and silent under a sky full of stars. But even in this darkness, there is light. The two companion stars provide a soft illumination comparable to the full moon on Earth, enough to see by, enough to cast faint shadows across the frozen landscape. And above you, the universe would be on full display, with no nearby star to wash out the sky. The night side of Gissa 667 cc would have some of the clearest, most spectacular views of the cosmos imaginable. Galaxies, nebulae, star clusters, all visible with a clarity that most humans on Earth have never experienced. It is a haunting image, a world of extremes, split between eternal fire and eternal ice, with a narrow ribbon of twilight offering the only hope of balance. It is alien and strange and utterly unlike anything in our experience. And yet, it is real. This world exists. It is out there right now, orbiting its dim red star, its companion stars, wheeling slowly through the distant sky, its terminator zone bathed in perpetual amber light. Let us shift our focus now and talk about something that is fundamental to whether this planet could ever support life. The atmosphere. We do not know if Gissa 667 cc has an atmosphere. That might sound surprising given everything we have discussed, but the truth is, our instruments are not yet sensitive enough to detect the atmosphere of a planet this size and this far away around a faint star. What we can do is think about what kinds of atmospheres are possible and what each scenario would mean for the planet's habitability. If Gissa 667 cc has no atmosphere at all, the picture is pretty grim. Without an atmosphere, there is no way to redistribute heat from the day side to the night side. The day side bakes, the night side freezes. There is no air to breathe, no protection from radiation, no liquid water anywhere on the surface. The planet would be a barren, airless rock, similar in many ways to our own moon or Mercury. But if the planet does have an atmosphere, things get much more interesting. An atmosphere acts like a blanket, trapping heat and spreading it around. Even a thin atmosphere could make a significant difference in how habitable the terminator zone is. A thicker atmosphere, similar to Earth's, could potentially distribute heat widely enough to make large portions of the planet's surface livable. However, the composition of the atmosphere matters just as much as its thickness. If the atmosphere is mostly carbon dioxide, as it might be for a planet this size in this location, it could create a strong greenhouse effect. This could be good or bad, depending on how strong the effect is. A moderate greenhouse effect could warm the planet to comfortable temperatures. Too strong, and you get a runaway greenhouse effect like what happened on Venus, where surface temperatures soar to over 400 degrees Celsius, hot enough to melt lead. There is another possibility that scientists have considered. Because Gissa 667 cc is more massive than Earth, it has a stronger gravitational pull. This means it could potentially hold onto a thicker atmosphere, including heavier gases. Some researchers have suggested that the planet might support an atmosphere with 2 or more times the surface pressure of Earth's atmosphere. This kind of dense atmosphere would be very effective at redistributing heat and could make the planet more uniformly warm. But it could also create uncomfortably high pressures at the surface, making it feel like living at the bottom of a deep ocean. The question of whether the planet has a magnetic field is closely tied to the atmosphere question. As we discussed earlier, without a magnetic field, the atmosphere is vulnerable to being stripped away by stellar winds and flares. But there is some nuance here. Even a slow-rotating planet can generate a magnetic field if its interior is hot enough to keep part of its core molten. And on a super-Earth like Gissa 607 cc, the interior pressures are higher than on Earth, which could help maintain a molten core even with slow rotation. Some scientists have proposed that tidal heating, the same process that threatens to melt the planet's mantle, could actually help maintain a magnetic field by keeping the core active. It is a paradox of sorts. The very thing that could make the surface uninhabitable could also provide the protection needed to keep the atmosphere intact. Nature loves these kinds of contradictions. There is yet another factor to consider. Red dwarf stars are known for a characteristic called star spots. These are similar to sunspots on our sun, but they can be much larger in proportion to the star's surface. Star spots can reduce the star's brightness by as much as 40% for extended periods. Imagine living on a planet where your sun suddenly dims by nearly half and stays that way for weeks or months. The temperature would drop. Weather patterns would shift. Any ecosystem adapted to a certain level of light and warmth would be thrown into chaos. For life on Gissa 667 cc, this kind of variability would be a serious challenge. On Earth, life has adapted to seasonal changes in light and temperature, but those changes are predictable and follow a regular cycle. The dimming caused by star spots is much less predictable and could be much more extreme. Any life that evolved on this planet would need to be remarkably resilient and adaptable. Speaking of life, let us talk about what kind of life could potentially exist on a world like this. Now, this is where we move firmly into the realm of speculation, and it is important to be upfront about that. We have no evidence of life on Gissa exoplanets. We have no evidence of life on any planet outside our solar system. What we can do is think about the conditions on this planet and ask whether life as we understand it could potentially thrive there. On Earth, life needs three basic things: liquid water, a source of energy, and the right chemical building blocks. Everything else, oxygen, sunlight, moderate temperatures, these are all helpful but not strictly necessary. We know this because life on Earth has been found in some of the most extreme environments imaginable. Microbes living in boiling hot springs, organisms thriving in the crushing pressures of the deep ocean floor, bacteria surviving inside rocks, miles beneath the surface, with no access to sunlight at all. If Gissa 660m-cc has liquid water in its terminator zone, that checks the first box. The energy from the star, even though it is mostly infrared, will provide a source of energy for potential photosynthetic organisms. And the chemical building blocks, carbon, hydrogen, nitrogen, oxygen, and others, are common throughout the universe. There is no reason to think they would be absent from this planet. But life on Gissa 667cc would look nothing like life on Earth. The dominant light from the star is red and infrared. On Earth, plants are green because they absorb red and blue light and reflect green. But on a world where most of the light is red and infrared, plants, if they existed, might evolve to absorb as much of that available light as possible. Scientists have speculated that vegetation on red dwarf planets could be dark in color, possibly even black, to maximize light absorption. Imagine a landscape covered in dark, almost black plants, spreading across the twilight zone like a living carpet, soaking up every photon they can from the dim red sun sitting on the horizon. Animals, if they evolved, would likely have very different senses than we do. On Earth, our eyes are tuned to the visible light spectrum because that is where our sun puts out the most energy. On Gissa 667cc, creatures might evolve eyes that are sensitive to infrared light. They would see a world that is invisible to us, a world of thermal signatures and heat patterns. A warm-blooded creature would glow in the infrared, making it easy to spot against a cooler background. Hunting and foraging could be guided by temperature rather than visible light. The constant twilight of the terminator zone would create unique ecological niches. There would be no daily cycle of light and dark to set biological clocks. Instead, the environment would be defined by geography, your position relative to the day side and night side. Organisms might migrate short distances toward or away from the warmth, following the temperature gradient like a compass. The ecology could be arranged in bands, with different communities of life at different temperatures, stretching from the warm inner edge of the terminator zone to the cold outer edge. If there were oceans or large lakes in the terminator zone, they could support aquatic life. The water would be warmed from one side by the nearby day side and cooled from the other by the night side, creating strong currents and upwellings. These currents could bring nutrients from deep water to the surface, supporting a rich food chain. It is not hard to imagine an underwater ecosystem in the twilight zone of Gissa, cc, thriving in waters that are warmed by infrared light and stirred by the planet's unique temperature dynamics. But we need to be careful here. It is tempting to paint vivid pictures of alien ecosystems, but we should always remember that these are stories built on the scaffolding of science, not confirmed discoveries. They are possibilities, not certainties. The value of this kind of thinking is not that it tells us what is there, but that it helps us understand what could be there and what to look for when our technology catches up to our imagination. Let us now zoom out and put Gissa 667 in context. Where does this planet sit among all the other potentially habitable worlds we have found? Since the early 1990s, astronomers have discovered more than 5,000 planets orbiting other stars. Some of these are gas giants many times larger than Jupiter, orbiting so close to their stars that their atmospheres are being stripped away. Others are tiny, rocky worlds, hidden in the glare of their parent stars, barely detectable by our best instruments. Among these thousands of worlds, a handful have been identified as potentially habitable. These are planets that sit in the habitable zones of their stars, that have masses and sizes consistent with rocky composition, and that receive amounts of energy comparable to what Earth gets from the Sun. Gissa 606 was one of the first to join this exclusive club. When it was confirmed in 2012, it held the record for the highest Earth similarity index of any known exoplanet. Since then, other strong candidates have emerged. Proxima Centauri b, for example, orbits the nearest star to our solar system, just 4.2 light-years away. TRAPPIST-1b and TRAPPIST-1f orbit a red dwarf about 40 light-years away in a system that has 7 rocky planets, 3 of them in the habitable zone. Kepler 442b and Kepler 452 have also been flagged as potentially habitable. But Gissa 667 cc remains special for several reasons. First, it is relatively close to us. At 23 light-years, it is one of the nearest potentially habitable worlds we know of. Second, it is part of a triple star system, which gives it a unique character that none of the other candidates share. Third, its host star is one of the most stable types in the universe. Red dwarfs like Gissa 667c can burn steadily for over 100 billion years. If life were to take hold on one of its planets, it would have an almost unimaginable amount of time to evolve. On Earth, complex life took about 4 billion years to develop. Around Gissa 667c, there would be time for that process to play out 10 or 15 times over. This longevity is both a blessing and a curse. On one hand, it means there is more time for life to emerge and evolve. On the other hand, it means the star will be around for a very long time, and so will its flares, its star spots, and its radiation. Any life that survives on a red dwarf planet would need to endure these challenges not for millions of years, but for billions. Only the most resilient forms of life would have any chance of making it. And this brings us to a deeper question, one that goes beyond the specifics of Gissa 606 cc and touches on something more fundamental. What does it mean for a planet to be habitable? When astronomers use the word habitable, they are using it in a very specific technical sense. They mean a planet where liquid water could potentially exist on the surface, given the right atmospheric conditions. This is a useful working definition, but it is also very narrow. It says nothing about whether life actually exists there. It says nothing about whether the planet has an atmosphere, a magnetic field, the right chemistry, or any of the other 1,000 things that might need to be true for life to get started. On Earth, we know of only one example of life arising. one single instance, as far as we can tell, in the entire history of our planet. And from that one example, we have tried to extrapolate general rules about what life needs. But what if life on Earth is not typical? What if the conditions that created life here are extraordinarily rare, and most planets that look habitable by our definition are actually lifeless? Or alternatively, what if life is much more resilient and adaptable than we think, and it can arise under conditions that would seem impossible by Earth standards? These are open questions, some of the biggest open questions in all of science. And Gissa 667cc, sitting out there in the constellation of Scorpius, bathed in the light of 3 stars, is one of the places where we might someday find answers. Let us take a moment now to appreciate something about the system as a whole, because the story of Gissa 667cc is not just the story of one planet. It is the story of an entire system of worlds. When astronomers first started studying Gissa 667c, they found evidence for 3 planets. But as they gathered more data and developed better analysis techniques, the picture grew more complex. By 2013, a team led by astronomer Mikko Tuomi at the University of Hertfordshire announced evidence for up to 7 planets orbiting this small red star. 3 of them appeared to be super-Earths sitting within the habitable zone. Now, this was extraordinary. No other star had been found with 3 potentially habitable planets. The habitable zone of Gissa 667c appeared to be fully packed. There was no room for any more planets in stable orbits within the zone. It was as if nature had filled every available slot. However, and this is important, subsequent studies have cast doubt on some of these additional planet claims. The signals that looked like planets might instead be artifacts of noise and stellar activity in the data. More careful analysis suggested that only 2 planets could be confidently confirmed: Gissa 667cb and Gissa 667cc. The others remain unconfirmed, and some scientists think they may not exist at all. This is how science works. Discoveries are announced, challenged, refined, and sometimes overturned. It can be frustrating for those of us who want clear, definitive answers. But it is also the process that ensures we get as close to the truth as possible. The fact that some of the claimed planets around Gissa 667c might not be real does not diminish the importance of the ones we know are there. It just means we need to be careful about what we claim and humble about what we know. Gissa 667c Batsur, the inner planet, orbits much closer to the star than CC. It takes only about 7 days to complete one orbit, and it is almost certainly too hot for liquid water. Its temperature would be far above the boiling point, making it more like a scalding oven than a habitable world. But CC, sitting farther out in the sweet spot of the habitable zone, remains our best hope in this system. Now let us address the elephant in the room. The distance, 23 light years. It sounds so manageable. After all, the Milky Way is 100,000 light years across. 23 is nothing in comparison. But when you translate that distance into human terms, it becomes staggering. Light itself, the fastest thing in the universe, takes 23 years to travel from Gissa 667 to Earth. If you could somehow build a spaceship that traveled at the speed of light, the journey would take 23 years. You would leave as a young adult and arrive in middle age, but we cannot travel at the speed of light. We are not even close. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour. That is absurdly fast by everyday standards, but the speed of light is about 670 million miles per hour. The Parker Solar Probe travels at about 0.06% the speed of light. At that rate, reaching Gissa 667 would take over 350,000 years. Our more typical interplanetary spacecraft, like Voyager 1, travel even slower, at about 38,000 miles per hour. Voyager 1 has been flying through space since 1977, and it has only covered about 1/390th of a single light year. At Voyager speed, reaching Gissa 667 would take nearly 400,000 years. To put that in perspective, 400,000 years ago, our ancestors were not yet anatomically modern humans. They were Homo heidelbergensis, a species that had not yet developed language, art, or agriculture. The idea of launching a mission that would not arrive until long after our species might have evolved into something unrecognizable is both humbling and mind-bending. There are theoretical propulsion systems that could do better. Nuclear pulse propulsion, the concept behind the old Project Orion designs, could potentially push a spacecraft to about 10% of the speed of light. At that speed, the journey to Gissa 667 would take about 230 years. Still many human lifetimes, but at least within the realm of something a civilization could attempt with a generation ship, a spacecraft designed to house entire communities of people who would live, reproduce, and die during the voyage, with their descendants eventually arriving at the destination. Other concepts, like laser-propelled light sails being explored by the Breakthrough Starshot initiative, could potentially accelerate tiny probes to 20% of the speed of light. At that speed, a probe could reach Gissa 667 in about 115 years. But these probes would be incredibly small, barely more than computer chips with tiny cameras, and they would fly past the system at tremendous speed, with only a brief window to take pictures and send data back to Earth. The hard truth is that barring some revolutionary breakthrough in physics or engineering, no human being alive today will ever visit Gissa 600, and possibly no human being ever will. This is a destination that exists for our telescopes and our imaginations, not for our bodies, and there is something both sad and beautiful about that. But let us not dwell on the sadness of distance. Let us instead focus on what we can learn from right here on Earth, using the incredible tools that human ingenuity has created. The James Webb Space Telescope, launched in December of 2021, is the most powerful space telescope ever built. It observes the universe primarily in infrared light, which makes it ideally suited for studying the kind of cool, faint stars that red dwarfs like Gissa 667c represent. While the telescope has been focused on many targets since its launch, its capabilities could in theory be applied to studying the atmospheres of nearby exoplanets. If Gissa 667cc transits its star, meaning it passes between the star and our line of sight from Earth, the telescope could potentially detect the fingerprints of atmospheric gases as starlight filters through the planet's atmosphere. Unfortunately, Gissa 667cc was discovered through the radial velocity method, not the transit method. This means we detected it by watching the star wobble, not by watching the planet cross in front of the star. For a planet to transit, its orbit needs to be aligned just right so that it passes between us and the star. The odds of this alignment depend on the size of the star and the distance of the planet's orbit. And for Gissa 667cc, the probability is relatively low. So while James Webb could in principle study this planet's atmosphere, it may not get the chance unless the geometry is right. But there are other ways to learn about this system. Future telescopes, both on the ground and in space, will have even greater sensitivity and resolution. The extremely large telescope, currently under construction in Chile, will have a mirror nearly 40 meters across. That is over 5 times the diameter of any existing telescope. With this kind of light-gathering power, it may be possible to directly image planets around nearby stars, separating the faint light of the planet from the overwhelming glare of the star. If we can do that for Gissa 667c, we could potentially measure the spectrum of light reflected from its surface and atmosphere, telling us what gases are present, what the temperature is, and even something about the composition of the surface. There are also proposed space missions that could revolutionize our understanding of nearby exoplanets. The Habitable Worlds Observatory, a mission concept being studied by NASA, would be specifically designed to image and characterize Earth-like planets around nearby stars. If this mission moves forward, planets like Gissa 667cc would be prime targets. These are not science fiction dreams. These are real projects with real budgets and real teams of scientists and engineers working to make them happen. Within the next few decades, we may have the ability to look at Gissa 667cc and say with confidence whether it has an atmosphere, whether that atmosphere contains water vapor, and whether there are any signs of biological activity. That would be one of the most profound discoveries in human history. Now let us circle back to something we touched on earlier, because it deserves a deeper exploration. The question of water. Water is, as far as we know, essential for life. Every living thing on Earth, from the smallest bacterium to the largest whale, depends on water. It is the medium in which the chemistry of life takes place. Cells are filled with it. Proteins fold in it. DNA replicates in it. Without water, the molecular machinery of life simply cannot function. This is why the concept of the habitable zone is built around water. The habitable zone is defined as the distance from a star where the temperature is just right for liquid water to exist on a planet's surface. Too close, and the water boils away. Too far, and it freezes solid. Gissa 667c sits comfortably within this zone, receiving about 90% of the energy that Earth gets from the Sun. The temperature math works out. Liquid water should be possible, but possible and present are very different things. For water to exist on the surface of Gissa 667cc, the planet needs water in the first place. Where would it come from? On Earth, water arrived through a combination of processes. Some of it was present in the dust and gas that formed the planet. Some was delivered later by comets and asteroids that smashed into the young Earth, carrying water ice from the outer solar system. If a similar process occurred in the Gissa 667 system, then the planets there could have received water deliveries from their own comets and asteroids. The composition of the Gissa 667 system gives us some clues. The system has a relatively low metallicity, meaning it has a lower abundance of elements heavier than hydrogen and helium compared to our Sun. Metallicity affects the formation of planets and the materials available to build them. Lower metallicity could mean less rocky material and potentially less water ice in the outer system, but it does not rule it out entirely. Water is made of hydrogen and oxygen, two of the most common elements in the universe. There is no reason to think the building blocks of water would be absent. Even if water was present when Gissa 667cc formed, keeping it is another matter. As we discussed, the star's flares and radiation could strip the atmosphere over time, and with it, any water vapor in the atmosphere. If the planet lost its atmosphere early in its history, any surface water would have evaporated into space and been lost forever. However, if the planet managed to hold on to its atmosphere, water could be remarkably persistent. Water that is deep underground or frozen on the night side would be protected from radiation. Volcanic activity could release water vapor from the interior, replenishing what is lost. And if the atmosphere is thick enough, it could trap water and prevent it from escaping. There is also the intriguing possibility of water being present in unusual forms. On Earth, we think of water as liquid oceans, frozen ice caps, and atmospheric vapor. But on a tidally locked super-Earth, water might behave very differently. The day side could have thick, steamy atmospheres where water exists primarily as vapor. The night side could have vast glaciers of ice. And in the terminator zone, liquid water could exist in sheltered valleys and basins, fed by the slow melting of night-side glaciers as they inch toward the warmer regions. Some scientists have proposed the concept of an eyeball planet to describe this kind of world. Imagine looking at the planet from space. The day side directly beneath the star would be a dry, hot desert, perhaps with a large spot in the center where temperatures are highest, like the pupil of an eye. Surrounding this hot spot, the landscape would gradually cool as you move toward the terminator zone. At the terminator, there could be a ring of liquid water, like the iris of the eye, and beyond that, the night side would be a vast sheet of white ice. Seen from above, the planet would resemble a great cosmic eye, staring back at the star that created it. It is a striking image, and it is one that scientists have used to help conceptualize what tidally locked habitable planets might actually look like. Whether Gissa 607cc fits this model depends on factors we cannot yet measure, but the possibility is tantalizing. Let us now talk about something that does not get enough attention when we discuss potentially habitable planets, the concept of time. We have talked about how Gissa 667c could burn for over 100 billion years. That is a staggering number, but it is hard to really appreciate without some context. Our Sun is about 4.5 billion years old, and it has about 5 billion years of fuel left before it begins to die. In that time, life on Earth has gone from simple single-celled organisms to the extraordinary diversity we see today. Humans have existed for only about 300,000 years, a tiny sliver of the planet's history. Our civilization, with its cities and technologies and space telescopes, is only about 10,000 years old, a mere heartbeat in cosmic time. Now imagine a star that could burn for 100 billion years. If a planet around that star developed life at the same pace Earth did, complex life could appear, go extinct, and appear again dozens of times over. Civilizations could rise and fall, and rise again, each one building on the ruins of the last or starting from scratch, depending on the circumstances. The amount of evolutionary experimentation that could take place over such a vast timescale is almost beyond comprehension. But there is a catch. Red dwarfs do not age gracefully. In their youth, they are highly active, flaring frequently and bombarding their planets with intense radiation. This violent phase can last for the first 1 to 2 billion years of the star's life. During that time, any planet in the habitable zone would be pummeled by flares that could strip atmospheres, sterilize surfaces, and create conditions hostile to life. Scientists estimate that the Gissa 667 system is at least 2 billion years old, and possibly 6 billion years old. If the system is on the older end of that range, then Gissa 667c may have already passed through its most active phase. The flares would have calmed down, the radiation would have decreased, and conditions for life would have improved. If the planet managed to hold onto its atmosphere through the early tumult, or if it rebuilt an atmosphere afterward through volcanic outgassing, then the current conditions might actually be more favorable for life than they were in the past. This is an important point. When we talk about habitability, we should not think of it as a static condition. Planets change over time. Stars change over time. The habitability of a world is not a permanent label. It is a snapshot of a particular moment in a long and evolving story. Gissa 667 cc might have been uninhabitable 2 billion years ago and habitable now. Or it might be the opposite. The only way to know is to look more closely, with better instruments and more sophisticated models. Let us explore another fascinating aspect of this planet's existence, its relationship with its siblings in the system. We know that Gissa 660 the inner planet, orbits the star every 7 days. It is much too close and much too hot for life, but its gravitational influence on Gissa 660 is significant. The two planets interact gravitationally, tugging on each other as they orbit. This interaction affects the shape and orientation of their orbits over time. For Gissa 667 cc, this gravitational dance causes its orbital eccentricity to change on a cycle of about 4.5 years. Sometimes the orbit is nearly circular. Other times it becomes more stretched out, more elliptical. This variation might seem minor, but it has real consequences. A more eccentric orbit means the planet swings closer to and farther from the star during each revolution. When it swings closer, it gets warmer. When it swings farther, it cools down. This creates a kind of superseason, a cyclical variation in temperature that plays out not over months, as Earth seasons do, but over years. The gravitational interaction between the two planets also contributes to the tidal heating we discussed earlier. As Gissa 667 c's orbit flexes and changes shape, the planet is stretched and squeezed by gravitational forces. This generates friction inside the planet, heating its interior. Over long periods of time, this heat can accumulate, potentially affecting the planet's geology, volcanism, and even its chances for life. In our own solar system, we see a similar process at work on one of Jupiter's moons, Io. Io orbits close to Jupiter and is gravitationally influenced by the other large moons, Europa and Ganymede. The resulting tidal heating makes Io the most volcanically active body in the solar system. Its surface is constantly being reshaped by eruptions of molten rock. If something similar is happening on Gissa 667 cc, the planet could be extremely geologically active, with volcanoes erupting regularly and tectonic forces reshaping the landscape. From a habitability standpoint, moderate geological activity is actually a good thing. On Earth, volcanoes release gases like carbon dioxide and water vapor into the atmosphere, helping to regulate the climate over millions of years. Tectonic activity drives the carbon cycle, which keeps atmospheric carbon dioxide at levels that maintain a comfortable temperature. Without plate tectonics, Earth might have followed Venus's path toward a runaway greenhouse, or Mars's path toward a thin, cold atmosphere. So if Gissa 667 cc has moderate geological activity driven by tidal heating, it could actually help maintain a stable climate and atmosphere. The key word is moderate. Too much activity, and the surface could be covered in lava flows and volcanic gases. Too little, and the climate regulation fails. Like so many aspects of habitability, it is all about balance. This brings us to an idea that runs through the entire story of Gissa 667 cc, like a thread. The idea that habitability is not about perfection. It is about balance. Earth is not a perfect planet. It has ice ages. It has mass extinctions. It has supervolcanoes and asteroid impacts and global shifts in climate that wipe out most of the life on the planet. And yet, life persists. Life on Earth has survived 5 major mass extinction events, each one killing off a majority of species. After each catastrophe, life bounced back, diversified, and became more complex. The resilience of life on Earth suggests that once it gets started, it is very hard to stop. If life is similarly resilient on other worlds, then the challenges facing Gissa 677cc, the flares, the tidal heating, the extreme temperature differences, might not be deal breakers. They might be obstacles that life finds ways to overcome, just as life on Earth has overcome ice ages and asteroid impacts. Imagine microbial life in the rocks beneath the surface of the Terminator Zone, protected from radiation by a few inches of soil. Imagine extremophile organisms in thermal vents where tidal heating creates warm, mineral-rich water. Imagine communities of simple life forms in sheltered valleys living in a perpetual twilight, slowly evolving over billions of years in the gentle glow of a red dwarf star that will burn long after our sun has died. It is speculative, yes, but it is speculation grounded in what we know about life's tenacity on Earth. And it is the kind of speculation that drives science forward, because it gives us hypotheses to test and questions to answer. Let us take a moment to appreciate something about the Scorpius constellation, where this system resides, because it connects our story to thousands of years of human history. Scorpius is one of the oldest recognized constellations. The ancient Sumerians saw the scorpion in these stars over 5,000 years ago. The ancient Greeks wove it into their mythology, telling the story of the scorpion that killed the mighty hunter Orion. In the sky, Scorpius and Orion are placed on opposite sides of the heavens. When one rises, the other sets. They are forever separated, the hunter forever fleeing the creature that ended his life. For most of the human history, when people looked at Scorpius, they saw mythology. They saw stories about gods and heroes and creatures of legend. They had no idea that hidden among those faint points of light was a system of 3 stars with a planet that might, just might, support life. There is something poetic about that. The same stars that inspired stories of myth and adventure are now inspiring stories of science and discovery. The human impulse is the same. Look up at the sky. Wonder what is out there. Tell stories about it. The only thing that has changed is the tools we use to tell those stories and the depth to which we can probe the mysteries of the cosmos. Now, let us get back to the science and talk about a concept that is relevant to Gissa 667cc and to every potentially habitable planet we have ever found. The concept is called the Fermi paradox, and it asks a simple but profound question. If the universe is so vast and so old, and if the conditions for life are not extraordinarily rare, then where is everybody? The Fermi paradox is named after the physicist Enrico Fermi, who supposedly posed this question over lunch in 1950. The logic goes like this. There are hundreds of billions of stars in our galaxy. Many of them have planets. Some of those planets sit in habitable zones. The galaxy is over 13 billion years old. If life can arise on habitable planets, and if some of that life eventually becomes intelligent and develops technology, then there should be civilizations out there that are millions or even billions of years ahead of us. They should have had time to spread across the galaxy. We should see evidence of them. Radio signals, megastructures, visits. And yet, as far as we can tell, the universe is silent. We see no evidence of other civilizations anywhere. This is the paradox. There are many proposed solutions to the Fermi paradox. Maybe life is much rarer than we think. Maybe intelligent life is common, but civilizations tend to destroy themselves before they can spread to the stars. Maybe the distances between stars are simply too great for any civilization to overcome, no matter how advanced. Maybe we are just not looking in the right way. Or maybe we are the first civilization in our galaxy to reach this level of awareness, the first to look up and wonder. Gissa 606cc sits right in the middle of this question. Here is a planet that seems to have many of the ingredients for life, orbiting a star that will burn for 100 billion years, in a system that is cosmically close to us. If life can arise on a planet like this, then the universe should be teeming with life. Red dwarfs are the most common type of star, making up about 70 to 80% of all stars in our galaxy. If even a small fraction of them have habitable planets, the total number of potentially life-bearing worlds would be in the billions. And yet, we have heard nothing. No signals from Gissa 667. No signals from anywhere. Just silence. Some scientists have proposed that the answer to the Fermi paradox might lie in the specific challenges that red dwarf planets face. The radiation, the tidal locking, the flares. These might be enough to prevent complex life from ever evolving, even if simple microbial life gets started. In 2017, a paper used statistical analysis to argue that if Earth is a typical habitable planet, then there must be some constraint that prevents habitability around stars with less than about 65% of the Sun's mass. Since Gissa 667c has only about 31% of the Sun's mass, this constraint, whatever it is, could significantly reduce the chances of life there. But this is just one argument among many. Other scientists are more optimistic, pointing to the recent discoveries about polar flare patterns and the possibility of atmospheric retention even around active red dwarfs. The debate continues, and it will likely continue for a long time, until we have the observational tools to settle it. What is certain is that Gissa 667cc represents one of the most important test cases in this debate. If we can determine that this planet has an atmosphere, has water, or shows any signs of biological activity, it would have profound implications for our understanding of life in the universe. And if we determine that it does not, that it is a barren, lifeless rock, despite sitting in the habitable zone, that would be equally important. It would tell us something fundamental about the challenges facing life around the most common type of star in the cosmos. Either way, Gissa 667c has something to teach us, and either way, the search is worth pursuing. Let us take a pause now and do something different. Let us use our imagination. Let us pretend, just for a few minutes, that we could actually visit Gissa 667cc. That some miraculous technology has carried us across 23 light-years of space, and we are there, standing on the surface of this alien world. What would it be like? You step out of your spacecraft and onto solid ground. The first thing you notice is the gravity. It is about 20% stronger than what you are used to. You feel heavier. Your legs have to work a little harder. But it is manageable. You can walk, run, even jump, though you will not get as high as you would on Earth. The second thing you notice is the sky. And here is where the experience becomes truly otherworldly. The star, Gissa 667c, hangs before you, massive and red and eerily still. It does not rise. It does not set. It just sits there, a huge disk of deep crimson, dominating the horizon if you are near the terminator zone, or hanging directly overhead if you are on the day side. It is like staring at a hot coal the size of a small plate, held at arm's length. The light it casts is warm but dim, painting everything in shades of red and orange and shadow. If you hold your hand up in front of you, your skin looks darker, more ruddy. Colors you are used to seeing are muted or changed entirely. That white shirt might look pinkish. A green leaf, if such a thing existed here, might look almost black. The air, assuming there is air, might feel thick and warm, especially on the day side. The atmospheric pressure could be higher than Earth's, maybe twice as high, which would make sounds travel differently. Your voice might sound deeper, richer. The wind, if there is wind, could carry a low hum as it moves across the landscape. On a planet with a dense atmosphere and strong temperature, gradients between the day side and night side, powerful winds could blow constantly, funneling heat from the warm side to the cold side. Looking around the landscape, you might see rocks and terrain that look somewhat familiar. Super-Earths are expected to have rocky surfaces, though the specific geology would depend on the planet's composition and history. If tidal heating has been significant, you might see signs of volcanic activity, fields of cooled lava maybe, vents in the ground releasing steam or gases. The ground might be warm beneath your feet, heated not just by the star above, but by the geological forces below. If you are near the terminator zone, the landscape could be extraordinary. Imagine standing in a valley where one wall catches the red light of the star and the other wall is in shadow. Ahead of you, the land rises toward the night side, where glaciers of frozen gases gleam faintly in the starlight. Behind you, the terrain slopes down toward the day side, where heat shimmers rise from the sun-baked surface. And right where you stand, in this narrow band of twilight, the temperature is comfortable, maybe a little cool, the kind of temperature where you would want a light jacket but nothing more. If there is water here, this is where you would find it. A stream, maybe, fed by melting ice from the night side, flowing through a channel carved over millions of years. The water would be cold and clear, catching the red light of the star and shimmering with an otherworldly glow. Pools and small lakes might dot the landscape, their surfaces still and reflective, mirroring the strange sky above. And that sky. Look up. In one direction, the red star. In another direction, darkness, punctuated by the brilliant points of Gissa, 667a and 667b. Those two companion stars that orbit each other far away. They look like two bright jewels, much brighter than any star we see from Earth, but still just points of light. Together, they cast a gentle illumination across the land like permanent moonlight, and scattered across the rest of the sky, thousands upon thousands of stars. With no light pollution from cities, no atmospheric haze from industrial activity, the starscape would be breathtaking. The Milky Way would stretch across the heavens, its billions of stars creating a river of light from one horizon to the other. And somewhere in that river, if you knew exactly where to look, you would find a small, unremarkable yellow star. Our sun, our home, 23 light years away. Close enough to see with the naked eye, but impossibly far for our feet to carry us back. If you stood there long enough, you might notice that nothing changes. The star does not move. The shadows do not shift. The companion stars drift slowly, but their motion takes years to become apparent. Time feels different on a tidally locked world. Without the rhythm of day and night, without the passage of the sun across the sky, time becomes shapeless, elastic. You would need to invent new ways to mark its passing, new rhythms to give structure to your days. This is the reality of Gissa 667 cc. A world where time stands still, where the light never changes, where the only rhythm is the one you bring with you. It is profoundly alien and profoundly beautiful. Now let us come back to reality and talk about something that I think is one of the most important aspects of this whole story. The idea that Gissa 660 c serves as a mirror. Not a literal mirror, of course, but a conceptual one. When we study this planet, we are really studying ourselves. We are asking questions about what makes a planet habitable, what conditions life needs, how resilient life can be. And those questions, at their core, are about us. They are about understanding our own planet and our own existence in a broader context. When we look at Gissa 667 cc and see a world that might have liquid water, we are reminded of how precious water is on our own world. When we consider the challenges of radiation and flares, we are reminded of how fortunate we are to have a magnetic field and an ozone layer protecting us. When we think about the tidal locking and the extreme temperature differences, we are reminded of how delicate the balance is on Earth, how our moderate climate depends on a long chain of fortuitous circumstances. Every exoplanet we study teaches us something about Earth. And Gissa 667 cc, with its triple stars and its tidally locked rotation and its terminator zone of eternal twilight, teaches us perhaps the most important lesson of all, that the conditions we take for granted, the blue sky, the warm sun, the air we breathe, the water we drink, these are not inevitable. They are the result of specific circumstances, a particular star, a particular orbit, a particular atmosphere, a particular magnetic field, all working together to create the narrow set of conditions that allow us to exist. This does not mean we should despair at how special Earth is. It means we should appreciate it. And it means we should keep looking, keep searching, keep studying planets like Gissa 667 cc, because every discovery, every piece of data, every model and simulation brings us closer to understanding our place in the universe. Let us talk more about red dwarfs, because understanding these stars is key to understanding the future of astrobiology and planet hunting. Red dwarfs make up somewhere between 70 and 80% of all stars in the Milky Way. That is an astonishing number. Look up at the night sky, and most of what you see are brighter stars, the kinds that stand out against the darkness. But for every bright star you can see, there are dozens of dim, cool red dwarfs hiding in the blackness, too faint for your eyes to detect. They are the silent majority of the galaxy. Because red dwarfs are so common, and because their habitable zones are close and relatively easy to study, they have become prime targets for exoplanet research. The transit method, which detects planets by watching them pass in front of their stars, works particularly well for red dwarfs because the dimness of the star makes the planet's shadow proportionally larger and easier to detect. The radial velocity method also works well because the planets in the habitable zone orbit close enough to create larger wobbles in the star's motion. As a result, many of the most exciting exoplanet discoveries in recent years have involved red dwarf systems. TRAPPIST-1, with its 7 rocky planets, orbits a red dwarf. Proxima Centauri b, the closest known potentially habitable exoplanet, orbits a red dwarf, and Gissa 667 cc orbits a red dwarf. This means that the question of whether life can exist around red dwarfs is not just an academic question. It is one of the most consequential questions in all of science. If the answer is yes, then the universe could be teeming with life because red dwarfs and their planets are everywhere. If the answer is no, then the prospects for finding extraterrestrial life are significantly diminished. because the other types of stars that might host habitable worlds are much less common. This is part of what makes Gissa 666 so important. It is not just one planet orbiting one star. It is a representative of a class of worlds that could number in the billions across our galaxy alone. Understanding this one planet could unlock insights that apply to countless others. Let us spend some time now thinking about what it means for a world to have 3 stars in its sky, because this is one of the most distinctive features of Gissa 667c, and it deserves more attention. We are used to thinking of solar systems as having one star. That is our experience. We have one sun, and all the planets orbit around it. It seems simple, clean, orderly. But the truth is, our situation might be the minority. Studies of nearby stars suggest that a significant fraction of star systems in our galaxy are binaries or higher order multiples. Many stars come in pairs or triplets, bound together by gravity, orbiting each other in complex patterns. Living on a planet in a triple star system would create a sky unlike anything we have ever experienced. On clear nights on the dark side of Gissa 667cc, the 2 companion stars would be the dominant features of the sky, bright enough to read by. They would slowly orbit each other over the course of about 42 years, their apparent separation changing subtly from year to year. Sometimes they would be close together, almost like a double star. At other times, they would be farther apart, 2 distinct points of light. These companion stars would have no significant effect on the planet's climate. They are simply too far away. At 230 astronomical units, their warmth would be negligible, but their light would matter. On the night side, their combined brightness could create a twilight-like glow, a gentle illumination that would prevent the night side from being truly dark. This could have implications for any life that might exist there. Even organisms living in the permanent night of the dark hemisphere would have some light available to them. Not enough for photosynthesis, perhaps, but enough to influence behavior, navigation, and evolution. For any intelligent beings that might someday evolve on Gissa 667 cc, the triple star system would profoundly shape their understanding of the cosmos. We humans developed our understanding of astronomy by watching the sun, moon, and stars move across our sky in predictable patterns. On a tidally locked planet with 3 stars, the astronomical patterns would be completely different. The primary star would never move. The companion stars would drift slowly over decades. The background stars would be visible from the night side, but not the day side. This alien astronomy would lead to a very different understanding of the universe, different constellations, different myths, different science. It makes you wonder, if intelligent beings evolved on a world like Gissa 667c, would they even develop astronomy as a science? On Earth, the daily motion of the sun and the monthly phases of the moon gave us natural timekeeping tools that help spur the development of mathematics and science. On a tidally locked world with no sunrise or sunset, no phases, no seasons, the motivation and the means to study the sky would be very different. Perhaps they would develop their understanding of the cosmos in ways we cannot even imagine. Let us now return to the practical science and discuss what happens next. What are the next steps in studying Gissa 667cc? And what should we hope to learn? The immediate priority is to better constrain the planet's properties. Right now, we know its minimum mass, its orbital period, and its distance from its star. But we do not know its exact mass, because the radial velocity method only gives us a minimum. The actual mass depends on the tilt of the planet's orbit relative to our line of sight, which we do not know. If the orbit is close to edge on, the true mass is close to the minimum. If the orbit is more tilted, the planet could be significantly heavier. We also do not know the planet's radius. For planets detected by the transit method, we can measure the radius directly from the amount of light the planet blocks. But Gissa 611 cc was not detected by transits. Without the radius, we cannot calculate the planet's density, which would tell us whether it is rocky like Earth or gassy like Neptune. Future observations might help. If we are lucky, the planet might transit its star, and we just have not observed at the right time. Systematic monitoring of Gissa 611 c with sensitive instruments could detect a transit if the geometry allows it. Alternatively, direct imaging with next-generation telescopes could detect the planet's light directly, giving us information about its atmosphere and possibly its radius. Beyond that, the Holy Grail would be to detect biosignatures, chemical signs of life, in the planet's atmosphere. On Earth, the presence of oxygen, methane, and ozone in our atmosphere is a strong indication of biological activity. These gases are not stable in our atmosphere on their own. Without life constantly producing them, they would disappear relatively quickly. If we detected similar gases in the atmosphere of Gissa 607 cc, it would be powerful, though not conclusive, evidence of life. Detecting biosignatures is incredibly challenging, especially for a planet that may not transit its star. It requires separating the faint light of the planet from the much brighter light of the star, and then analyzing that faint light for the spectral fingerprints of specific molecules. Current technology cannot do this for a planet like Gissa 667 cc, but the telescopes being built and planned right now are designed with exactly this capability in mind. Within the next 2 to 3 decades, we may have the tools we need. Let us now talk about something that rarely gets discussed in these kinds of conversations, but that I think is deeply important: the emotional significance of places like Gissa 667 c. We live in a time of extraordinary discovery. In the span of a single human generation, we have gone from knowing of no planets beyond our solar system to knowing of thousands. We have photographed the surfaces of Mars, the geysers of Enceladus, the dunes of Titan. We have seen the rings of Saturn in exquisite detail and peered at the atmospheres of planets orbiting distant stars. We are living through the golden age of planetary exploration, and yet, there is a loneliness to all of this. Every world we have studied up close, Mars, Venus, Mercury, the moons of Jupiter and Saturn, has turned out to be inhospitable, beautiful, fascinating, scientifically valuable, but lifeless as far as we can tell. Earth remains the only known harbor of life in the universe. This loneliness is part of what makes planets like Gissa 667 cc so compelling. They represent hope. The hope that somewhere out there the conditions are right, that somewhere the chemistry has clicked, that somewhere in the twilight zone of a world orbiting a red dwarf star, something is alive, even if it is just a microbe, even if it is just a patch of dark-colored lichen clinging to a rock in the dim red light. That hope is not naive or unscientific. It is grounded in the observation that life on Earth is incredibly tenacious. It exists in the boiling springs of Yellowstone and in the ice sheets of Antarctica. It exists in the crushing depths of the Mariana Trench and in the thin air high above the Earth's surface. It exists in solid rock, in salt deposits millions of years old, in pools of acid, and in the cooling systems of nuclear reactors. If life can thrive in all of these extreme environments on Earth, then perhaps, just perhaps, it can find a way on other worlds too. And if it can, Then Gissa 607 cc, with its liquid water potential, its moderate temperatures, its ancient star, and its vast reserves of time, is as good a place to look as any. Let us spend a few more minutes imagining the night side of this world, because it is perhaps the most mysterious part of the entire planet. If you could somehow survive on the night side of Gissa 607 cc, you would experience a landscape of otherworldly beauty and silence. The ground beneath your feet would be frozen solid, not just water ice, but possibly frozen carbon dioxide, nitrogen, even oxygen, depending on the atmospheric composition. These frozen gases would form smooth, pale surfaces that stretch to the horizon, reflecting the faint light of the companion stars. The temperature would be far below anything experienced on the Earth's surface. Even the coldest place on Earth, Antarctica's interior, only drops to about 90 degrees below 0 Celsius. The night side of a tidally locked planet could be hundreds of degrees colder than that. At these temperatures, the air itself might freeze, creating a thin atmosphere, or no atmosphere at all in the coldest regions. But even in this frozen wasteland, there could be pockets of interest. If tidal heating is strong enough, volcanic vents could poke through the ice, creating small oases of warmth and liquid water. These would be similar to the hydrothermal vents on the floor of Earth's oceans, which support thriving ecosystems in complete darkness, powered not by sunlight, but by the chemical energy of hot mineral-rich water. Imagine a volcanic vent on the night side of Gissa 607 cc. Steam rising from a crack in the ice, the warm water melting a small pool around it. In the faint light of the companion stars, this pool would glow softly, a tiny spot of warmth in a vast desert of cold. Could life exist in such a place? On Earth, similar environments support bacteria, worms, shrimp, and other organisms. There is no reason in principle why something similar could not happen elsewhere. The night-side glaciers could also play an important role in the planet's overall water cycle. As we discussed earlier, ice from the night side could slowly migrate toward the terminator zone, driven by the temperature gradient. This slow flow of frozen water, imperceptible on human timescales, but significant over millions of years, could continuously feed liquid water to the twilight zone, sustaining any bodies of water that exist there. In some models, the night-side glaciers could be enormous. Imagine a sheet of ice stretching for thousands of miles from the Interstellar point, the spot directly opposite the star, all the way to the terminator zone. This ice sheet would be one of the defining features of the planet, a vast white expanse on one side contrasting with the dark, warm terrain of the other. From space, this contrast would be dramatic. The day side would be dark, rocky, maybe reddish from the star's light. The terminator zone would be a thin band of varied terrain, mountains, valleys, rivers, lakes. And the night side would be a vast white cap of ice, reflecting the distant starlight like a mirror. This brings us to another thought experiment. What if, far in the future, humanity did find a way to reach Gissa 607 cc? What would we do when we got there? Science fiction has explored this idea in many ways, but the practical reality would be extraordinary and challenging in equal measure. The terminator zone, with its moderate temperatures and potential water supply, would be the natural place to establish a settlement. The narrow band of habitable land would create a unique form of civilization, one that extends in a line around the entire planet, rather than spreading across a wide surface as it does on Earth. Housing and infrastructure would need to be designed for a world with no day-night cycle. There would be no need for windows oriented to catch the morning sun. Instead, all structures might face the perpetual horizon glow, or they might be sealed and artificially lit to create a more Earth-like environment inside. Energy would be abundant. The star's infrared radiation could be harnessed using specially designed solar panels optimized for the red and infrared spectrum. The constant illumination means no nighttime, no cloudy interruptions on the dayside, just a steady, reliable stream of energy. The temperature difference between the dayside and nightside could also be exploited for power generation, using the same principles that drive heat engines on Earth. Agriculture would be fascinating. Earth crops are adapted to the full spectrum of sunlight, including blue and green wavelengths that are scarce in the light of a red dwarf. Growing Earth plants on Gissa 667 cc would require either artificial lighting or the development of new crop varieties adapted to the available light. Alternatively, if native life existed on the planet, local organisms adapted to the red light could potentially be cultivated. The social and psychological effects of living on a tidally locked world would be profound. Humans have evolved with a strong circadian rhythm, an internal clock set to a roughly 24-hour cycle of light and dark. Without any external cues to maintain this rhythm, settlers would need artificial lighting cycles within their habitats to avoid the health problems associated with disrupted sleep patterns. Depression, fatigue, cognitive impairment, all of these are risks that astronauts and researchers in polar regions already face during extended periods of continuous light or darkness. But humans are adaptable. We live in the Arctic, where the sun does not rise for months at a time. We live on submarines, where there is no natural light at all. We live on the International Space Station, where the sun rises and sets 16 times a day. Given time and the right technology, humans could adapt to life on a tidally locked world. It would be different, strange, but possible. Of course, all of this is far beyond our current capabilities. We cannot even get a probe to Gissa 667 cc, let alone a colony ship. But thinking about these possibilities is not just a fun exercise. It helps us understand the planet better, because it forces us to think about the details of habitability in ways that pure astronomy does not. Let us come to what I think is the most profound tension at the heart of this whole story. The thing that makes Gissa 667 cc both endlessly fascinating and deeply bittersweet. It is the paradox of proximity. 23 light years. In the context of a galaxy that is 100,000 light years across, this is practically next door. If you drew a map of the Milky Way and put a pin where we are, and another pin where Gissa 667 is, you would need a magnifying glass to see any gap between them. We are neighbors, cosmic next-door friends. And yet, those 23 light years might as well be 23 million. We cannot cross that gap, not now, maybe not ever. The fastest thing in the universe, light itself, takes 23 years to make the trip. A radio signal sent from Earth right now would arrive at Gissa 667 in 2049, and any reply would not reach us until 2072. A conversation with even a single exchange would span nearly half a century. For a spacecraft, the journey is almost unimaginably long. At the speed of Voyager 1, our fastest interplanetary probe, the trip would take roughly 400,000 years. Even with the most optimistic near-future technology, nuclear pulse propulsion that might achieve 10% of light speed, the journey would take over 200 years, multiple human lifetimes, longer than any nation on Earth has lasted without fundamental transformation. This is the cruel arithmetic of interstellar space. The distances are so enormous that they dwarf every achievement of human engineering, We can split atoms, we can sequence genomes, we can build telescopes that see 13 billion years into the past. But we cannot cross the void between the stars. Not yet. And this is where the paradox bites hardest, because Gissa 666 is one of the most tantalizing objects in the sky, a world that might support life, a world with liquid water, moderate temperatures, a stable orbit, and an ancient star that will keep shining for tens of billions of years. It is right there. We can study it with our telescopes. We can build models of its climate and map the boundaries of its terminator zone. We can calculate the height of its tides and the intensity of its star's flares. We can almost taste the alien air, but we cannot go there. We cannot stand on its surface and feel the warmth of its red sun. We cannot dip our hands in its waters or watch its strange sky for signs of life. This is a world that is close enough to see, but too far to reach, a paradise behind glass. And it is not just Gissa 666. Every potentially habitable exoplanet we have ever found is locked behind this same barrier. Proxima Centauri b, 4.2 light-years away. TRAPPIST, 1R, 40 light-years away. Kepler, 4142b, over 100 light-years away. We can study them, model them, dream about them. But we cannot visit them, not with any technology that currently exists or that we can reasonably foresee in the near future. This is perhaps the defining frustration of our time. We are the first generation of humans to know that other, potentially habitable worlds exist. We can see them across the void, shimmering with possibility. But we are imprisoned by the speed of light and the limitations of our engineering. We are like explorers standing on a mountaintop, seeing distant lands spread out below them, knowing they exist but unable to descend the cliffs. And yet, I would argue that this frustration is also a gift, because the knowledge itself is transformative, even without the ability to visit. Think about what it means to know that Gissa 667cc exists. It means that the laws of physics allow for worlds like this to form. It means that somewhere 23 light-years away, there is a place where the temperature might be right for water to flow. It means that the universe is not just a collection of dead rocks and burning gas. It is a place where the conditions for life can emerge, where the chemical building blocks of biology can find their way to the right temperature at the right distance from the right kind of star. That knowledge changes everything. It changes how we see ourselves, how we see our planet, and how we see our place in the cosmos. Even if we never visit Gissa 667cc, knowing it is there expands our understanding of what is possible. It pushes the boundaries of our imagination and inspires us to keep looking, keep studying, keep asking the big questions. Now let us talk about what I call the cosmic mirror effect, because I think it is the most beautiful idea to come out of this entire exploration. When we study Gissa 667c, we are not just learning about an alien world. We are learning about ourselves. Every measurement we make, every model we build, every question we ask about that distant planet reflects back on our own world and forces us to see it with new eyes. Consider the atmosphere. When we ask whether Gissa 660cc has an atmosphere thick enough to redistribute heat and maintain liquid water, we are implicitly acknowledging how important Earth's atmosphere is for our own survival. The thin layer of gas surrounding our planet, just a few dozen miles thick, is the only thing standing between us and the vacuum of space. It keeps us warm, provides the air we breathe, shields us from radiation, and distributes heat from the equator to the poles. Without it, Earth would be as lifeless as the moon. And yet, we take it for granted. We pump greenhouse gases into it without thinking about the consequences. We thin the ozone layer and wonder why skin cancer rates are rising. Studying the fragility of potential atmospheres on exoplanets like Gissa 667 cc reminds us of the fragility of our own. Consider the magnetic field. When we worry about whether Gissa 667 cc can generate a strong enough magnetic field to protect its atmosphere from stellar winds, we are implicitly recognizing the vital role that Earth's magnetic field plays in our own survival. The magnetosphere is invisible and intangible. You cannot feel it, you cannot see it without special instruments. And yet, it deflects streams of charged particles that would otherwise strip away our atmosphere and bombard the surface with lethal radiation. Consider the water. When we speculate about whether liquid water might exist in the terminator zone of Gissa 667 cc, we are implicitly celebrating the abundance of water on Earth. Our planet has so much water that from space it appears blue. 70% of the surface is covered in it. It falls from the sky. It flows in rivers. It fills oceans that are miles deep. We drink it, swim in it, sail on it, and are made of it. And yet, in the context of the universe, this abundance of liquid water might be extraordinarily rare. Most of the water in the cosmos is frozen solid in comets and on the surfaces of moons. Finding it in liquid form in the right temperature range on a rocky planet in the habitable zone might be one of the rarest and most precious configurations of matter in existence. Gissa 667 cc holds a mirror up to all of this. It shows us what a world looks like when these things are uncertain, when the atmosphere might not be there, when the magnetic field might be too weak, when the water might be locked in ice or boiled away to steam. And in seeing that uncertain, precarious world, we see our own world more clearly. We see how remarkable it is that everything came together on Earth, how every piece of the puzzle fell into place. This does not mean Earth is unique. There might be millions of planets out there that are just as fortunate. But it does mean that what we have here is precious. It means that our blue skies and flowing rivers and breathable air are not inevitable. They are the product of a very specific set of circumstances, and they deserve to be valued and protected. Let us now look at this from a slightly different angle. The angle of cosmic loneliness. One of the deepest human emotions is loneliness. The feeling of being alone, of being the only one, of having no one out there who understands. And in the cosmic sense, humanity might be profoundly alone. We have searched for signals from other civilizations for over 60 years now, and we have found nothing. Not a whisper, not a flicker, just silence. Gissa 667 cc represents one of our best hopes of breaking that silence. Not necessarily because intelligent beings live there, but because even the discovery of microbial life, even the detection of a biosignature in the atmosphere, would tell us that we are not alone, that the process that created life on Earth can happen elsewhere, that we are not an accident or a fluke, but part of a larger pattern of life that stretches across the galaxy. That discovery, if it comes, would be one of the most important moments in human history. It would change philosophy, religion, art, science, and politics. It would reshape our sense of who we are and where we fit in the grand scheme of things. And it could happen within our lifetimes if we invest in the right telescopes and the right research. But what if the answer is no? What if we look at Gissa 616 c and every other promising planet and find nothing? What if the universe really is empty of life except for us? That too would be a profound discovery. It would mean that what happened on Earth is rare beyond measure, that the process of life arising from non-living matter is so unlikely that, In a galaxy of hundreds of billions of stars, it has happened only once. That would make life on Earth, and human consciousness in particular, the most remarkable phenomenon in the known universe. Either way, the search is worth it. Whether we find life or do not find life, we learn something fundamental about our place in the cosmos, and that knowledge in itself is worth the effort. Let us now bring our exploration of Gissa 667 ZTC to a close with some final reflections. Throughout this journey, we have covered a lot of ground. We have traveled 23 light years to a world orbiting a dim red star in a triple star system. We have explored the extreme environments of the day side, night side, and terminator zone. We have considered the challenges of radiation, tidal locking, and atmospheric retention. We have imagined what life might look like in the ruddy twilight of an alien world. And we have confronted the profound distances that separate us from this and every other potentially habitable planet. Along the way, we have tried to be honest about what we know and what we do not know. The truth is, for all the math and modeling and educated speculation, we cannot yet say whether Gissa 667 cc is truly habitable. We cannot say whether it has an atmosphere, water, a magnetic field, or life. These are questions that future generations of scientists will need to answer, using telescopes and techniques that have not yet been built. But what we can say is that this planet represents something important. It represents the possibility that the universe is not hostile to life, that the conditions for biology are not confined to one small blue planet orbiting one ordinary yellow star, that the laws of physics and chemistry, the same laws that govern every atom in our bodies, can produce habitable worlds in the most unexpected places, around dim red stars, in triple star systems, on tidally locked worlds that never see a sunrise. The title of this journey asks whether scientists have discovered planets so habitable they could replace Earth. And the honest answer is not exactly. Gissa 660 cc is not a replacement for Earth. It is something different, something alien and strange and wonderful in its own right. It is a world that challenges our assumptions about what habitable means and forces us to think bigger, wider, and more creatively about the possibilities for life in the universe. Could you live there? Probably not, at least not without extraordinary technology. Would you want to visit? Absolutely. Even knowing the challenges, even knowing the radiation and the tidal locking and the dim red light, there is something irresistibly compelling about a world where 3 stars hang in the sky and the twilight never ends. And that brings us to perhaps the most important point of all. The mystery of Gissa 667 cc is not something to be feared or dismissed. It is something to be explored. The fact that we do not know all the answers yet is not a failure of science. It is the very engine that drives science forward. Every question we cannot answer today is a question that motivates the research, the funding, the telescope construction, and the international cooperation that will bring answers tomorrow. Science is a process of exploration, and every exploration begins with wonder. The wonder of looking up at the night sky and asking, what is out there? The wonder of finding a planet that checks so many boxes for habitability and asking, could life exist there? The wonder of imagining a sky with 3 stars and asking, what would it be like? That wonder is what brought us here tonight. That wonder is what drives the search for life beyond Earth. And that wonder is what makes planets like Gissa 667 cc so important, not just as scientific curiosities, but as reminders of the vast, beautiful, mysterious universe we are privileged to be part of. There is one more thing I want to leave you with before we wrap up, and it is about time. not cosmic time or geological time, but your time. Right now, tonight, as you listen to this, wherever you are, whatever you are doing, take a moment to look up. If you can see the sky, look at the stars. If you cannot see the sky, close your eyes and imagine them. Somewhere up there, in the direction of Scorpius, about 23 light years away, there is a small red star. And around that star, there is a planet. It is about 4 times the mass of Earth. It orbits in 28 days. It has 3 stars in its sky, and it might, just might, have the conditions to support life. You cannot see it. No one can, not with the naked eye. But it is there, right now, at this exact moment, orbiting its dim red sun, bathed in infrared warmth, its terminator zone caught in eternal twilight. Whatever is happening on that world, whether it is a barren rock or a thriving ecosystem, it is happening right now, in real time, 23 light years away. And here is the thing that gets me every time I think about it. The light we see from Gissa 667 tonight left that system 23 years ago. When that light began its journey, it was the early 2000s on Earth. The world was a different place. And yet, the light traveled faithfully across the void, carrying with it information about a star and its planets, waiting to be collected by our telescopes and decoded by our science. There is something deeply humbling about that. The universe is constantly sending us messages, beams of light from every star in the sky, each one carrying data about a distant world. All we have to do is build the instruments to listen and the wisdom to understand what we hear. So tonight, as the world quiets down and the stars come out, remember Gissa 667 cc. Remember that 23 light years away, there is a planet that reminds us of everything wonderful and mysterious about the universe we live in. Remember that the search for life beyond Earth is one of the noblest pursuits of human civilization. And remember that every time you look up at the sky and wonder, you are participating in that search, because the universe is vast and we are small, but our curiosity is boundless, and that makes all the difference. Now here is a thought to carry with you as you drift off tonight, or go about the rest of your evening. The star Gissa 667c will keep burning for over 100 billion years. Long after our sun has swelled into a red giant and swallowed the inner planets, long after the Earth has been reduced to a charred cinder, long after every trace of human civilization has been erased by the passage of time, that little red star will still be there, glowing quietly in the darkness, its planets still orbiting, its terminator zones still caught in their eternal twilight. If life exists on Gissa 667 cc, it could persist for tens of billions of years longer than life on Earth will last. Whatever evolves there, if anything does, will have more time to grow, change, and develop than life on Earth will ever have. The story of that world, if it has a story, could be 100 times longer than ours. There is something both comforting and humbling about that idea. Comforting because it means life, if it exists there, has an extraordinary amount of time to flourish, and humbling because it reminds us that our own story, the story of life on Earth, is just one chapter in a much larger book. A book that the universe is still writing, one star system at a time. Before we go, let us revisit something we talked about near the beginning, the importance of being honest about what is speculation and what is established fact, because in a world of clickbait headlines and exaggerated claims, this matters more than ever. When we say Gissa 667 CT is potentially habitable, We are not saying it is inhabited. We are saying the conditions are right for liquid water, based on the planet's distance from its star and the energy it receives. That is a real, measurable thing. But everything beyond that, the atmosphere, the water, the life, is inference and speculation. Does that mean it should not be explored? Absolutely not. Scientific speculation, when it is grounded in data and clearly labeled as speculation, is one of the most powerful tools we have. It generates hypotheses, it guides research, it points telescopes in the right direction. Without speculation, we would never make new discoveries, because we would never know where to look. The key is to be honest about what we know and what we are guessing. And when the evidence changes, we must be willing to change our minds. That is the heart of the scientific method, and it is what separates good science from wishful thinking. So when you hear about Gissa 667cc or any other potentially habitable planet, approach it with a mixture of excitement and skepticism. Get excited about the possibility, because the possibility is real and extraordinary, but also maintain a healthy skepticism about the details, because the details are uncertain and could change as we learn more. That balanced approach, excitement tempered by honesty, is the best way to engage with the incredible discoveries being made in astronomy right now. It allows you to appreciate the wonder without being misled by hype, and it prepares you for whatever the truth turns out to be, whether it confirms our hopes or challenges our expectations. Now, I want to talk about one last idea. The idea that the study of exoplanets like Gissa 667cc is not just about those distant worlds. It is about us, about our future, about the choices we make right now, here on Earth. Because here is the uncomfortable truth. We have exactly one planet that we know can support human life. One, not two, not 10, not a billion. One. And that one planet is under stress. Climate change, habitat destruction, pollution, resource depletion. These are not abstract problems. They are immediate, urgent challenges that threaten the long-term habitability of our own world. Studying Gissa 667cc will not solve these problems, but it can give us perspective. It can remind us how rare and precious a habitable planet is. It can show us, through the lens of an alien world, what happens when the conditions for life are uncertain, when the atmosphere is at risk, when the balance between too hot and too cold is razor thin. If nothing else, the study of exoplanets should make us better stewards of our own world, because out there, across the vast emptiness of space, there are billions of planets where the conditions are almost right. Almost. Close to habitable, but not quite. Planets that are too hot, or too cold, or too dry, or too irradiated. Planets that came so close to being like Earth, but fell just short. We live on the one that did not fall short. We live on the planet where everything came together. That is not something to take for granted. That is something to fight for. So here is my question for you as we bring this journey to a close. If you could trade our one sun for 3 stars, our regular days and nights for an eternal twilight, our blue sky for a dim red glow, would you? Would you trade the comfort of Earth for the mystery of Gissa 667cc? I think most of us would say no. And that is the right answer. But I also think that most of us would say we are grateful to know that Gissa 667cc exists. Grateful that the universe is rich enough and complex enough to produce worlds like this. Grateful that we have the intelligence and the tools to discover them. And grateful that the search for life beyond Earth continues, driven by the same curiosity that has propelled humanity from cave paintings to space telescopes. Thank you for joining us on this journey to Gissa 607 It has been a privilege to explore this world with you. If you enjoyed this exploration, please consider hitting that like button and subscribing to Cosmic Drift. We have so many more journeys planned, so many more worlds to discover, and we would love to have you along for the ride. Drop a comment below and tell us what you think. Would you want to live on a tidally locked planet? Do you think life exists on Gissa 607 What other worlds should we explore next? Until next time, keep looking up, keep wondering, and remember, somewhere out there, 23 light years away, a planet bathed in red light is waiting to be understood. And the only thing standing between us and that understanding is time, curiosity, and the willingness to keep searching. Good night and clear skies. Let us spend a little more time with the science of how we actually found this planet, because the story of the discovery itself is as remarkable as the planet it revealed. The instrument that made the discovery possible, HARPS, is a spectrograph, a device that takes the light from a star and splits it into its individual wavelengths, like a prism splitting white light into a rainbow. But HARPS does not just create a pretty rainbow. It measures the exact position of each wavelength with extraordinary precision. When a planet orbits a star and pulls it slightly towards us, the star's light shifts very slightly toward the blue end of the spectrum. When the planet's orbit carries it away, pulling the star away from us, the light shifts toward the red end. These shifts are tiny. We are talking about changes in the speed of the star of just a few meters per second, walking speed, and yet HARPS can detect them. Finding Gissa 670 required years of careful observation. The astronomers had to watch the star night after night, seasons after season, building up a data set of thousands of measurements. Each measurement told them how fast the star was moving toward or away from us at that moment. Over time, a pattern emerged, a rhythmic back and forth, like a heartbeat, with a period of about 28 days. That was the signal of the planet. But the star is not orbited by just one planet. There are at least 2 confirmed planets, and possibly more. Each planet creates its own wobble in the star's motion, and these wobbles overlap and interfere with each other. Extracting the signal of one planet from the noise created by the others is like trying to hear a single conversation in a crowded room. It requires sophisticated mathematical techniques and a great deal of patience. The initial claim of up to 7 planets was based on a statistical analysis of the wobble data. But other researchers, using different analytical methods, found that some of the signals might actually be caused by the star itself. Stars are not perfectly smooth, steady objects. They have spots and pulsations and convective patterns that can create small periodic variations in their light. These stellar noise signals can sometimes mimic the wobble caused by a planet, leading to false detections. This is why the number of confirmed planets around Gissa 667 has been revised downward from 7 to 2. It is not that the original astronomers were wrong. They were using the best methods available at the time. But as better methods were developed and the limitations of the data became better understood, the picture was refined. Science is self-correcting. It does not always get things right on the first try, but it has a built-in mechanism for finding and fixing its mistakes. The 2 confirmed planets, Gissa 667 and Gissa 667, are on solid ground. Their signals are strong, consistent, and have been confirmed by multiple independent analyses. We can be confident that they are real. Beyond that, the picture gets murky, and it will take future observations with more sensitive instruments to settle the question of how many planets this system truly hosts. Let us also talk about the constellation of Scorpius itself, because there is a connection between the mythology and the science that I find deeply appealing. Scorpius is one of the few constellations that actually looks like what it is named after. Its brightest star, Antares, is a red supergiant that marks the heart of the Scorpion. It glows with a distinctive orange-red color, cool and enormous, hundreds of times wider than our Sun. Below Antares, a chain of stars curves downward and then hooks back up, forming the Scorpion's tail and stinger. It is one of the most recognizable patterns in the southern sky. For ancient cultures around the world, Scorpius was a powerful symbol. The Mesopotamians saw it as a scorpion man, a guardian of the gates of the underworld. The ancient Egyptians associated it with Serket, the goddess of healing and protection. The Polynesians saw it as a giant fishhook, the same fishhook used by the demigod Maui to pull islands from the sea. And the Greeks, as we mentioned, connected it to the story of Orion. Now, hidden among these ancient patterns, invisible to every civilization that has ever looked up at these stars, is the triple system of Gissa 667, a tiny, faint collection of 3 stars that no human eye has ever seen directly. And around the smallest and faintest of those 3 stars, a planet that might be one of the most important worlds in the galaxy for understanding whether we are alone. There is a poetic irony in this. The ancients looked at Scorpius and saw death, danger, and the underworld. We look at the same stars and find a potential cradle for life. The same sky, the same stars, but a completely different story. A story not of gods and monsters, but of atoms and molecules and the improbable chain of events that can turn a cloud of dust and gas into a world where water might flow and life might stir. Let us also take a moment to consider the light from Gissa 667c as it reaches us. This is worth thinking about because light is not just a tool for seeing, it is a messenger. Every photon that arrives at our telescopes from that distant star has traveled for 23 years across the vacuum of space. It has passed through the thin gas between the stars, dodged dust grains, and finally entered the lens of a telescope high in the mountains of Chile, or floating in the cold of space above our atmosphere. That photon carries information. Its exact wavelength tells us about the temperature of the star's surface. Its brightness tells us about the star's size and distance. Any slight shift in its wavelength tells us about the motion of the star, and by extension, the planets that orbit it. In a very real sense, every photon is a letter in a cosmic message, and our instruments are the translators that turn those letters into words and sentences and paragraphs of knowledge. When we detect the wobble of Gissa 667c, caused by the gravitational pull of Gissa 667c, we are reading a message that was written 23 years ago by the planet itself. The gravity of that distant world, pulling on its star, imprinted itself on the light we received. It is a form of communication across interstellar distances. Not intentional, not conscious, but communication nonetheless. The universe speaking to us in the language of physics. And we have learned to listen. Over the past 3 decades, humanity has developed the ability to detect planets around other stars. We have gone from knowing of 0 exoplanets to knowing of over 5,000. Each one is a new data point, a new piece of the puzzle. And collectively, they are telling us something profound about the nature of the universe. Planets are common. Rocky planets in habitable zones are not exceedingly rare. The ingredients for life are widespread. The conditions for life, while specific, can be met in many different star systems. This is perhaps the most important insight from the study of exoplanets. Not any single discovery, but the cumulative realization that the universe is far more hospitable to life than we might have feared. Not everywhere, not easily, but in enough places with enough variety that the search for life beyond Earth is not a wild goose chase. It is a reasonable, scientifically grounded pursuit. And Gissa 607cc is one of the reasons we know this. Let us spend our final moments together contemplating the deep quiet of space, because at its heart, this is what cosmic drift is about. The quiet, the stillness, the vast peaceful emptiness between the stars where nothing happens and everything matters. Space is not really empty, of course. It is filled with dust and gas and radiation and magnetic fields and the faint hum of the cosmic microwave background, the echo of the Big Bang itself. But to human senses, it would feel empty, silent, still, a place where time seems to slow down and the worries of everyday life seem very far away. On a planet like Gissa 667cc, this cosmic quiet would be given form. The Terminator Zone, with its perpetual twilight and its unmoving star, would have a quality of timelessness that does not exist anywhere on Earth. No ticking clock of sunrise and sunset, no rushing to get things done before dark. Just the steady, warm glow of a red star, the slow drift of the companion stars across the sky, and the deep silence of a world that has been sitting quietly in the habitable zone of its star for billions of years. There is something calming about imagining such a place, a world where time has a different meaning, where the urgency of our lives gives way to the patient rhythm of a cosmos that measures time in billions of years rather than seconds and minutes, where the light never changes and the horizon is always the same, not static exactly, not lifeless, but still, peaceful, waiting. And maybe that is the most important thing Gissa 667cc can offer us right now, tonight. Not the hope of a second home or the discovery of alien life, though those things may come in time, but the gift of perspective, the reminder that the universe is vast and old and patient, and that our brief, busy, noisy lives are set against a backdrop of profound silence and beauty. So as you close your eyes tonight, or as you go about the rest of your evening, carry that image with you. A world bathed in red light, where the twilight never ends and 3 stars share the sky. A world that sits patiently in the habitable zone, orbiting its ancient star, waiting for someone or something to discover its secrets. A world that reminds us, if we let it, that the universe is full of wonders we have barely begun to explore. The night sky is a book with an infinite number of pages. We have read only a few of them so far, but the story is extraordinary. And Gissa 607cc is one of the most compelling chapters we have found. Thank you for being here. Thank you for listening. Thank you for wondering. The stars are waiting, and so are we. And perhaps that is the most beautiful part of the whole story, that we are a species that looks up, a species that wonders, a species that, despite all the challenges of daily life, still finds time to think about distant worlds and dream of what might be.